All right, let's get right into it. You've probably heard this, right? The entire AI boom. We're talking everything from ChatGPT to those crazy AI image generators. It's all running on hardware that was made for something totally different, video games. So, how in the world did a gaming chip end up powering this massive AI revolution?
I mean, the connection just seems random, doesn't it? You've got these blockbuster video games with insane graphics over here, and then you've got something like ChatGPT that can write a poem over there. But you know the hidden link between them? It all comes down to solving a very, very big math problem.
And here's the quick and dirty answer. It's all about a special kind of chip, the GPU, the graphics processing unit. Now, unlike a regular processor, a GPU is a master of parallelism. That's a fancy word, but it just means it's built to do thousands of simple things all at the exact same time. And well, it just so happens that's precisely what modern AI was desperate for.
Okay, so to really wrap our heads around this, we first have to talk about the huge problem at the core of AI. It's this massive calculation bottleneck.
So at its heart, an AI like ChatGPT is what's called a neural network. Just picture it as a bunch of layers, stacked one after another. When you type in a prompt, that data flows through the first layer, then the next, and so on. And here's the key part. Every single connection between these layers has a number attached to it, a weight, that changes the data as it goes along. Right, so here's the thing you really need to get. The entire learning process, the thinking that an AI does, it's really just a gigantic, mind-numbing series of multiplications. That's it. The input data gets multiplied by those weights, and then that result gets multiplied by the next layer's weights, and on it goes, sometimes through thousands of layers. It's all just matrix math, but on a ridiculous scale. And the scale, I mean, it's just wild. To push just one tiny batch of data through a deep network, we're not talking millions of users here, just one small batch, one time. That can take over 200 million multiplications. 200 million! Now try to imagine doing that thousands of times every single second for millions of people. It's just whoa. So yeah, that is the massive computational wall that AI developers slammed into. How on earth do you do a practically infinite number of simple multiplications as fast as is electronically possible? The old way of doing things? It just wasn't going to cut it. Not even close. So let's take a look at that old way, that traditional approach. We can call it the slow, sequential method. You know, it's the first way you'd probably think of to solve this, and it is unbelievably inefficient. Just imagine a normal computer processor, a CPU, trying to tackle this. It's like a really diligent worker, but it can only think about one thing at a time. It focuses on calculating the very first number in the answer. Then, once that's done, and only when that's done, it moves on to the second one, then the third. It's got a one-track mind, just chugging along one step at a time. And here's the really crazy part, the big inefficiency. While that processor is totally laser-focused on that one single calculation, all the other data, all the numbers it's going to need for the next steps, they're just sitting there, on the sidelines, doing absolutely nothing. It's such a massive waste of potential. The source material really nails it when it says this method is wasting a colossal amount of time simply because it's sequential. Think about it. It's like having just one checkout lane open at the grocery store, but there are 1,000 people in line. Sure, it'll get the job done eventually, but it is painfully, painfully slow. But then came the big aha moment, the breakthrough that honestly changed everything. And it all came down to one word: parallelism. The key insight was this, and it's brilliant. Turns out, calculating the number for one spot in the final answer has absolutely nothing to do with calculating the number for any other spot. They are all completely independent jobs. So the question just kind of slaps you in the face, right? If none of these calculations depend on each other, why in the world are we waiting around and doing them one by one? And this is where you see the solution in action. Forget one worker doing one task at a time. What if we had an entire army of workers and we gave each one a single cell to calculate and told them all to do it at the exact same time? And the difference, it's just staggering. Let's say our little 3x3 problem took 90 seconds to solve one by one. 10 seconds for each of the 9 calculations. Well, if you do it in parallel, the whole thing takes just 10 seconds total. That's not a small improvement. That's a 900% speed up. That's the magic of parallelism right there. Okay, so if parallelism is the answer, what kind of hardware is actually built to do this? And that brings us right to the big showdown, CPU versus GPU. So a CPU, that's your computer's main brain. It's like a master chef. You've got maybe a few super powerful cores that can whip up really complex gourmet dishes, but they do it one at a time. A GPU, though, that's a completely different beast. It's like a massive assembly line with thousands of simpler workers. Each worker does just one small, repetitive task, but they all do it at the exact same time. Or hey, think of it like this. A CPU is kind of like a regular two-lane road. It's great for getting a few cars to all sorts of different complex places. But a GPU is a 16-lane super expressway built for one thing and one thing only, handling thousands and thousands of cars, or, calculations, all moving in parallel, all at the same time. All right, so we've got this massive expressway with thousands of lanes. Great. But how do you actually direct all that traffic? How in the world do you get thousands of tiny little computer cores to work together without causing a huge mess? Well, the answer is a really cool concept called a kernel. A kernel is just a small, simple program, a single list of instructions. See, with a GPU, you don't write thousands of different programs for each core. No way. You write one program, the kernel, and then you basically blast it out to every single one of those thousands of cores and say, okay, everybody, run this now. So here's the master plan, how the GPU actually pulls this off. First, it arranges all its little cores into a grid, like a spreadsheet that perfectly matches the shape of the answer we need. Step 2, it gives each core its own unique assignment. Hey you're in charge of row 5, column 12. Then, step 3, it beams out that kernel, that one set of instructions to everybody. And finally, boom, it gathers up all the tiny individual results and pieces them together into the final answer, all in a fraction of a second. And what's so elegant about this whole system is just how simple it is. One individual core doesn't need to know what any of the other thousands of cores are doing. It doesn't care. All it needs are two little pieces of info from the main grid. Here's your row, and here's your column. That's it. With just that, it can do its one little multiplication completely on its own, independent of everyone else. So let's just recap the big takeaways here. At its heart, AI's biggest headache is a giant math problem. But luckily, it's a math problem that we can slice up into thousands of tiny independent calculations. And the GPU, which was first built to draw thousands of pixels all at once for video games, turns out to be the perfect tool for the job. And that kernel, that's the secret sauce, the master instruction that lets this whole army of cores work together in perfect sync. And that kind of brings us to a final, pretty cool thought. We just saw how a piece of hardware designed for something totally different got repurposed and became the key that unlocked this entire AI revolution. So it really makes you wonder, right? What piece of unexpected tech, something that's just sitting around in plain sight today, is going to be the key that unlocks the next revolution?